This recording is protected by copyright. No part may be reproduced without the prior permission of the University of South Australia.
Two topics. One of them hopefully will take 10 minutes or less, and the other will be the rest of the class. The first is, okay, how do we justify these? Well, with limits, okay? Because by the time we write these, that's the only way to justify them. By writing limits and showing that the formula on the right and the formula on the left, they have this, they come from the same type of limit, okay? But I'm not going to do that because you're not expected to do that in this course anyway. Instead, I'm going to show you how Leibniz did it. Okay? Nobody does it anymore. Leibniz was one of the two inventors of calculus, Newton and Leibniz. And Leibniz had a way of doing it, and Newton had another way of doing it, much more complicated, by the way. Okay? But here's Leibniz's way. You will remember that for Leibniz, if y is f of x, as we write today, the derivative for him would be dy divided by dx. Okay? And dy and dx, for Leibniz, the way he explained it, were these quantities that are very, very, very small, but not zero. How small? As small as you want to make them, but not zero. They are what he called infinitesimal quantities. And their fraction, dy divided by dx, is the derivative. And that's not an infinitesimal quantity. That's a number. A lot of baloney. Okay? It takes a lot of intellectual justification to come up with a correct statement, and that's not it. Okay? But Leibniz said, but it works, right? Okay? And what I'm going to say here is based on the following notion. 1 on 10 is small. But 1 on 10 times 1 on 10, which is 1 on 100, is very, very small. Okay? So if you get a small number and you square it, you get something that is an order of magnitude smaller. All right? So for instance, if you have a dx and multiply it by itself, dx times dx, a dx is small, so dx squared is going to be so small, you throw it away. All right? Okay? Okay. So here's how Leibniz did the product rule. I have a function, f of x, but I'm not going to write, and you want to multiply that by a function g of x, right? And I want to take the derivative of that. Okay? I'm going to give it a name. I'm going to call it f, g. Well, the next letter is age, but I don't want to call it age. I'm going to call it P for product, okay? I'm going to call it P for product. Now, here's the thing. If I change x to x plus dx, remember what we did not yesterday, but in the last class. We had x, and we added age, right? Or added delta x to it. And you move to x plus delta x. In here, I'm not adding the whole delta x, I'm adding just dx. If x changes from x to dx, from x to x plus delta x, then f changes to f plus df, g changes to g plus dg, p changes to P plus dP. If you increase the value of x by dx, everything changes a little bit. But this formula here has to still be true, meaning that P plus dP has to be equal to F plus dF G plus dG. Now multiply it. F times G plus F times dG plus dF times G plus dF times dG. But wait a moment, remember what I said? The dF is so small and the dG is so small, when you multiply them together, they get very, very small. Throw it out. So I'm not going to write. There's a missing term here that I'm not writing because it's too small. Okay? Now, P was Fg. So this guy here is P. And it cancels with the P on the other side. So you get the formula that dP is F dG plus dFG. Now if you divide everything by dx, and if you write it with a dash notation, you get the derivative of P. P is F times G. So the derivative of F times G is equal to the derivative of F times G plus F times the derivative of G. No limits. Just the only thing you really did is throw away a term that was too small, because dF is already an infinitesimal, right? So dF times dG is an infinitesimal, and an infinitesimal is 0. Throw it out. Okay? Of course, a lot of people got upset with that, but it works. If it works, right? So here is an exercise that you do after this course is finished, okay? So make absolutely no mistake, I'm not asking you to do it for the course. After the course is finished, okay? Prove this rule here, the quotient rule. Okay? Using that, so Q plus dQ is F plus dF, G plus dG, and good luck. Okay? I'll give you one more step. Q is F divided by G. So dQ is F plus dF divided by G plus dG minus F divided by G minus Q, right? And now reduce the same denominator and good luck. Okay? Newton had an even more complicated way of doing calculus. And in the 100 or so years after Newton and Leibniz, people developed the ways we're using now. All right. Okay, so here's the deal. We achieved something of great intellectual import, right? We can now compute slopes of tangent lines. Great. What do you do with it? Right? I did say here, let's use that as a motivation. What we want to do is compute slope of tangent lines. But why? Who cares? Can you do any more with that derivative thing? Okay. It turns out that, yeah, you can do a lot with it. The first application we're going to see is to maximization and minimization. And the deal is this. Okay? All right, so, so today's topic, max min. In Australia, with S or Z? S. I'll betray my origins. Okay? In this life, we often want to maximize or minimize quantities. You want to get the maximum amount of, candy for your dollar. You should give $5 to my son and say, go and buy some candy. And he spends quite some time in front of it, trying to get the most candy for $5 that he can get. Maximization is like, me, I try to minimize calorie with the same $5. Fantastic. We're always trying to do that. You want to get the shortest distance from here to the wall. You want to minimize the distance, right? It is common. Problems of maximization and minimization are everywhere. Okay? Nature likes to minimize energy. So if you're studying physics, there's something in there. Okay? How can you use derivatives to study that? Okay? Well, the deal is the following. Let's say that I have a quantity that is a function. Okay? Here's my x, here's my y, and I have a function like this. Oh, bad picture. Let's choose a better picture. Okay? And what I want to do is maximize the quantity y for different choices of x. All right? That's what I want to do. So you can pick any value of x you want. And you look at the corresponding value of y. And you ask, can I do better? Can I pick a value of y, or a value of x, that will give me even a better value of y? Okay? Honest question. Now, better, if you're maximizing, okay, is the highest possible value of y. Okay? In the picture I drew, it's here. There's no higher value of y. So this I'm going to call ym for maximum. And I'm going to call this xm for the maximum x that gives me the largest y. And it's capital M. Now, let's say I want to minimize. Choose the value of x that gives me the lowest possible value of y. Again, there may be none. Okay? But in this picture, there is one, because the lowest value of y is here. So I'm going to, this is the x I want, and this is the y I want. I'm going to call that ym, little m for minimum, and I'm going to call this x m, little m. Okay? The function f, in general, is going to be given by a formula, not by a graph. Okay? So if you want to find the maximum and the minimum, one way to go is, yeah. You have a question? That's it. No, only one derivative. Only one. That comes after, and it's related to it. But first, simple one first. Okay? Well, it's easier than what you said. Right? So let's see. Train of thought. Yes. So if a function is given as a formula, and all you know to do is to plot it, okay, then you have to plot it to decide who is max and who is min. But as I mentioned before in a previous class, one of the great advantages of calculus is that you can dispense with dispense with picture. You can do it without picture. Okay? Take a look at the picture here. Before we do without the picture, we need to take a look at it. And what you realize is the following. If you are either at the max or at the min, the slope is 0. Because the slope is horizontal. If you doubt it, can I have your book? If you doubt it, try to balance a book on your head. If you try to balance here, it's going to fall because it's sloping, right? You need to balance exactly at the top where the slope is 0. It's the max. You move it a little from the top, and how much is it? Yeah. Did you capture? Edit that. Edit that. Okay? At the very top, you are completely horizontal. The slope is 0. At the very bottom, the same. Okay? All right? So if you want to find, xm and xm, you should find all values of x for which the slope is 0. But I didn't write the slope is 0. I wrote the formula. Okay? All right? Let me reproduce this picture one more time. over here. Now, let's find every single value of x where the slope is 0. There's one here. There's one here. Another. And another. And another. And one more. And one more. So x1, x2, x3, x4, x5, x6, and in my picture, x7. There are 7 values of x. No, it's a picture, right? 7 values of x. Not everybody is the maximum. Not everybody is the minimum. There's only one maximum and only one minimum. Okay? I am not saying that when you solve this equation and find the 7 values of x, that everybody is going to be your answer. What I'm saying is that your answer is amongst those guys. Okay? In other words, solving this equation here will give you many different answers, one of which is going to be the max, one of which is going to be the min. Okay? All you know is that the slope is 0 there. All right? Now freeze that frame and let me throw a little confusing thing here for you. Even after you find these guys, there may not be max and min, because I didn't give you the full picture. Here's the full picture. Okay? Now, is there a max? No, there is no absolute max. There is no value of y that is the largest value, because it seems that it keeps going up, both that way and this way. Okay? There is a min, though, in my picture, which is here, an absolute min, which is a good time now, since you mentioned, to introduce some names here. The absolute max is the value of x, not the value of y, the value of x that gives you the largest possible y, if there is one. I'm going to write this down. Is the value of x which maximizes the function, the largest possible. So in this picture here, this is not an absolute max. This is not an absolute max, and this is not an absolute max. Okay? They are what we call a local max. In other words, they are the max, but just near them. Far away, there could be other. Okay? It's like near Adelaide, what's the largest mountain or hill? It's Mount Lofty. Mount Lofty, at the top of Mount Lofty, you are at the local max. But it's not the absolute or global max. The global max for Australia is Mount Kosciuszko. Can't get higher than that in Australia. The global max for the world is Mount Everest. Okay? But there are lots of local max. The top of any hill is a local max. The top of my head is a local max. The highest point around me. Right? And likewise, you have absolute or global. Likewise, you have absolute or global minimum. Okay? And local minimum. So in here, this is a local minimum. It's the x that gives you the thing. This is a local minimum. This is a local minimum. This is a local and global minimum. Okay? So that, with that little bit of nomenclature out of the way, these guys are going to be found by taking a derivative and equaling to 0. So let's do an example. Okay. And what I want to do is I want to find absolute and local max and min. So let's see. Here's what I do. I take a derivative of that. And then I set it equal to 0. I need to solve this equation. So I need to solve 2x take 6 equals 0. And I solve it. To find x equals 3. So even though I did not draw a picture, and I didn't even attempt to draw a picture, I can tell you right now that there's only one value of x that can be either a max or a min, and the value of x is 3. So if I were to draw a picture, okay, I put the x equals 3 there. By the way, I can plug in 3 here. I get 9, take away 18 is negative 9, plus 1 is negative 8. So I know that the height here is negative 8. So this is 3, negative 8. I know that the graph of this function goes through here, and I know that the slope is horizontal there. So that's the information I have. I know that the slope is going to be horizontal there. That's all I know. Now we have to complete a picture from here, right? How does it complete? Well, if I don't have any other if I'm a computer, okay, I don't know how to complete that picture unless I have very good software. But it could be like this, in which case it would be a local minimum. Let's draw these possibilities here. It could be like this, in which case it's a local minimum. It could be like that, in which case it's a local maximum. And now I'm going to do something that's extremely perverse. Okay? It could be like this. Wants to be a maximum, wants to be a minimum, and it's neither. It could be like this. Wants to be a minimum, wants to be a maximum, and it's neither. So bad news all around, right? You think you got something, but you see you got less than you thought. Solving the equation derivative equal to 0 gives you a value x equal 3, and by itself, you don't know. You don't know if it's max or min, max, or whatever it's called, inflection point, okay, or whatever. You need extra information, okay? You do need extra information before you decide that. In this case, there, it is going to be a local minimum. And in fact, now here it starts to be interesting, okay? Let's say you know it's a local minimum, okay? So you know that it's looking like this, right? Now, what happens far away? Well, you can't do this. You can't do this. Because if you do this, there is another value, x with derivative 0. And you know there aren't any, right? So it doesn't flip back. If it doesn't flip back, it has to keep growing. And then it keeps growing, and keeps growing, and keeps growing, and keeps growing. I don't know, maybe the growth is like this, or maybe the growth is like that. But it has to keep growing. So if you only have a little bit more information, not a little, it's quite a bit, but if you do, oh, then you start getting a lot more. Okay? Again, let me tell you what type of information we're using here. We're not only using that x equals 3 has slope 0, but it's the only guy with slope 0. Okay? So if it is this local min, growth on both sides. If it is a local max, it's going to be decay on both sides. If it is like this, on that side it grows, on that side it goes down. Okay? Because you don't have another one. How do you determine which one is which?
I'm going to say, could you, before you start to draw, probably do a line of best fit to work out where it's going to go down?
You can. That's one way to do that, okay? But that's more complicated than you need. Okay? There are two ways to try to determine if it is min or max, okay? We're going to study them in another class, not today. Right? But there are ways using the derivative to do that. I'll just say one thing. X equals 3 is the only spot where the derivative is 0, right? It's the only spot where the derivative is 0. So it's the only spot where you have slope that's horizontal. That means that if I pick a value for x that's bigger than 3, I'm not going to get 0. Do I get positive or negative? I don't know. But it makes a huge difference because positive slopes like this and negative slopes like that. So if I want to know if it's going up or if it's going down, I need to know if the derivative is positive or negative, and that is easy to do. So we'll talk about that later. Okay? If it hit a mark, great. If it didn't, it will hit the mark in another lecture. Okay, we'll come back to this important topic. Let's do a word problem. Oh, don't you like those? Word problems are great. I will start with the absolutely most classic possible word problem, which is like this. Two positive numbers. X, A and B add up to, give me a number. 7. Add up to 7. She picked it, not me, so don't complain. Add up to 7. What is the largest possible product between A and B? So you give me two positive numbers, and they add up to 7. Let's say 1 and 6. They add to 7. The product is 1 times 6, 6. Okay? Or you give me 3 and 4. They add up to 7. The product, 3 times 4, is 12, which is bigger than 6. Now, think of all possible values, not only integer values, but fractional values, whatever, that you can have for A and B, as long as they add up to 7. Okay? Well, what's the choice that you have that will give you the largest possible product? Okay? This problem is often phrased like this. I have a piece of string with length 7. Okay? Now, with my piece of string, I break it like this. So this is 7, but I pinched it here, right? And this is 90 degrees. So this is A, and that's B. How should I break it so that this area here is the largest possible area? Okay? Because the area is A times B, right? But it doesn't matter how I break it. A plus B is always going to be 7. Absolute classical problem. Every time you either teach or take a calculus course, that problem is there. Okay? Perhaps not with 7, but. So let's see. First thing I need to do, now I'm going to write down the steps for solving it, okay? Steps for solving. Step 1, identify the thing which you want, or that you want to maximize. I'm going to write optimize instead of maximize, because in certain problems it's maximize, in certain problems it's minimize. So I'm going to use a word that will represent both. Optimize. Okay? What in this problem here, does anybody want to volunteer? What do you want to optimize? Read the problem. What do you want to maximize? the product. Okay? The product. So you identified. You even going to say more if I didn't interrupt you. You're going to say the product between A and B. So you can write that in words. The product between A and B. That's the quantity. Or you can write it in formula. And that's preferred. You can do both. Okay? A times B. That's it. Okay? Now that's my function. That's the stuff I want to maximize. Unfortunately, as you will readily verify, very unfortunately, there are two variables there, A and B. And we can only do calculus in this course with one variable. So you have to eliminate one of them. Okay? Either I'm going to write A in terms of B, or I'm going to write B in terms of A. Has to be done. Okay? Is that all right? Two. If necessary, eliminate variables. It is just a way of saying write everything in terms of only one variable.
So you mean instead of saying all of the combinations, you say just all the combinations for A, like 1 times A?
No, that's not what I mean. When I show you what to do, you see. Okay? To eliminate a variable, ask yourself, is there any relationship between the variables that you know, A and B? Is there any relationship between them? They add up to 7. So we know that A plus B is 7. And that relationship allows me either to write A in terms of B or B in terms of A. In fact, it will not matter much because there is a symmetry in there, right? So choose which letter you like better. Do you like A better or B better? Let's hear it for A. Okay, A. So I'm going to eliminate B. I'm going to write B is equal to 7 minus A. That's what I mean by eliminate a variable or write one in terms of the other. Okay? But to be able to do that, you need to find a relationship between them that's not the stuff you want to maximize, not this one. There must be some other information in the problem that will allow you to do that. If the problem doesn't contain that information, the problem is not correctly written. Okay? Now, using this, I'm going to eliminate B from the previous one. So this is A, 7 take away A. That's step 3, but I wrote step 3 on the board. Okay? Step 3, use this relationship to simplify the target formula. Do I need to write step 3? I'm going to do it because you asked. Even though you didn't say anything, I can tell. No. Step 3. Use 2, which is this formula here, to simplify 1. Now you got an expression. The thing you want to maximize in terms of only one variable, okay? Only one variable. I'm going to write f of a here. F of a. A is my variable, not x, but a. I could have started by calling it x and y if I wanted, or you can call the two numbers anything you want. I called a and b, so it's f of a. So now let's see. Let's remember what we want to do. We want to maximize f of a. Which is the product, right? Maximize the product. Maximize that. Take a derivative and set it equal to 0. What's that? Yep. 7 take away 2a. 7 minus 2a. Negative 2a plus 7. That's it. And set it equal to 0. And when you solve, you'll find that a is 7 on 2. And once you know the value of a, you know the value of b. Which tells you the following. The best way to break these numbers so that their product is the largest possible is to make them equal, right? There's a symmetry in there, right? Well, how do you know it's a max? How do I know this is the max? Why isn't it the min, the smallest possible product? That would be, right? Why isn't it one of those guys that go up and then go up again? Important questions, right? Important questions. So let's take a look. Do you see that we got an answer here? It looks like A has to be 7 divided by 2, and B has to be 7 divided by 2. In other words, get your piece of string and divide it in half. And that will give you the largest area. Or get your two numbers and put half and half. 7 on 2, 7 on 2. Not 6 on 1, not 3 and 4. It's 3.5 and 3.5. That's what we'll do. And what's the product? What's the largest product? The largest product is going to be 7 on 2 times 7 on 2, which is going to be 49 divided by 4. If that is indeed the largest guy. Why isn't it the smallest guy? Why isn't it one of your other pictures? Well, that's for later. Okay? But here's a justification. A very brief justification. All right? What's the smallest value that the variable a can be? Can it be negative 10? Well, remember how I wrote the problem? I said, let a and b be two positive numbers that add up to. Okay? And when it's a piece of string, a is the length of a string, right? So it can't be negative. So the smallest value, well, it's 0, let's say. Let's pick a to be 0, the smallest guy. What's the largest value that a can be? Say it, say it. You're right. Say it because you're right. Say it loud. Who said it? 7. Right? You can't go above 7. So A goes from 0 to 7. This formula here, you can plug in any value for A. I can plug in A equal 20 in here. Okay? But the problem only admits values of A between 0 and 7. So 0 to 7 is a domain. Okay? From 0 to 7. Now, looking at the formula, if A is 0, how much is the product? 0 times 7, 0. If A is 7, the product is? Now, plug in 7 for A. What do you get? 7 times 0. Sorry, it's a bit tricky. Not the other one. So there you go, 0 and 0. Okay? If you're right in the middle, the value is 49 on 4. Okay? And I do know that slope here is 0. Right? Okay? Remember the 4 pictures you can have? The 4 pictures are, you can have a picture like this, a picture like that, a picture like this, and a picture like that. Okay? Now you have to fit one of these 4 pictures on these 3 points here. And you can see that the only picture that will fit is this. So it's got to be a max. It's got to be the largest. Okay? You can also see it because this is a parabola with negative concavity, so it has to be pointing down. So if you want to reason like that, you're fine. Okay? But you cannot fit any of the other pictures in there. If it were to be a max, okay, fine, no problem. But how do you get there? You must do this at some point. And as soon as you do that, there's another point of derivative of 0, but there was only one, so you can't. I beg your pardon, on Thursday, we're going to be doing almost 2 hours, I think, of word problems, one after the other, and practicing derivatives, practicing derivatives, practicing derivatives all the way. It's a must-attend tutorial, okay? Because maximize and minimize problems are the bulk of your exam and tests and everything, okay? Just love them. So do not miss that. We'll practice and practice and practice. And when you have a break, we'll practice more. Thank you for attending today, and I'll see you tomorrow. Bye-bye.